Hello physics fans and intellectuals. Today we're going to be talking about a very interesting topic that will surely excite your brain. So we're going to be talking about QWIPS, or quantum well infrared photodetectors. They're very applicable to military and to what we're going to do in the future, potentially, and we're going to dive into them. So come along and talk about QWIPS. The topic that we're going to be talking about is quantum well infrared detectors, or QWIPS, as I previously stated. QWIPS are conceptually pretty easy to understand once they're understood, but the process of getting from start to finish and understanding the concept does take a little bit of time. So, me, as your trusty guide, is going to teach you how QWIPS work quantumly, and therefore you're going to be able to understand them later. QWIPS have three really important things that everybody should understand. It's the band gap, the valence band, and the conduction band. Those three things are what's in the detector system, and from there we're able to understand basically how the electron moves between them. So, the valence band is the band where most of the electrons are going to be in a ground state. There's not really much going on with there as far as this concept is, but for time's sake, we're going to talk about it being the ground state. Next is the band gap. The band gap is how much energy requires the electron to jump from the valence band to the conduction band. The conduction band is where most of the excited electrons are going to reside. So now, since we understand the three basic things of the detector system, or things that are operating within the quantum well, we can go into the type of absorption that is dealt with in the QWIP. Before we dive into the actual applicable one, we're going to be understanding a more simpler one that is the foundation for what QWIPS apply to. So this process is called the interband optical absorption. The interband optical absorption has to do with a photon coming in, exciting that electron. The electron is then moved out most of its placement within the valence band, and then it has to jump to the conduction band. The photon that's coming in has to be greater than the energy of the band gap energy. When the electron leaves the valence band, it creates an electron hole. That electron hole, it's just like a missing electron. There's really not much to it, but it creates some type of current within that band. So, within that band, the current is being moved by photocarriers over the band gap and into the conduction band. That creates the photocurrent, as I said before, and there really isn't much doping required for this system because the missing electron within that valence band automatically creates the current and the energy source for it. So those are the main things that are consistent with it. So let's go over an overview to make sure that everything is understood. 3 bands: band gap, conduction band, valence band. Valence band is most of the ground state. Band gap is the energy state for the electron, for the proton to come in and create an excited electron. That excited electron leaves, creates a hole, and when it leaves and creates that hole, it also creates a current. That current is then moved by the photocarrier, and the photocarrier puts that electron into the conduction band. It's now in an excited state, and it creates the energy that's used for a QWIP. Simple as that. The application for the QWIP that is now being used is a smaller band gap. Scientists have found that the band gap is designated for specific types of photons. Those photons have a specific energy reading, and they correspond with a specific band gap. So what scientists did was make the band gap smaller and then have a distinct energy reading, or a more widely used energy reading for the photon to be picked up by the band gap or switched over. So that eliminates the small band gap main. With this all being said, the QWIP uses a different type of absorption, or at least a more applicable absorption when dealing with the smaller band gap. That's the inter-sub band gap. That means that bands are doped, which means there's a foreign energy state being put into the system that causes the electrons within each of those bands, meaning the conduction band and the valence band, to be excited but not have the electron be moved by photocarriers, which means that the electron is going to be staying within the respective band. That's what QWIPS use. QWIPS use that simple movement of I'm going to stay here, I'm going to be excited, and then that's it. There's no moving, there's no necessarily need for a band gap, and that's what they really eliminated. So the thing that's a little bit different when it comes to these specific absorption in the wells that we talked about, within those wells, there is a ground state. The ground state is simply described as the discrete energy function that is given away. That's how we really annotate it as. But the photon comes in within those wells, and while it's within those wells, it excites the electron. The electron then moves out of that well, and therefore it's going to be staying in that same band. So it's not moving into a different band, it's not even jumping a band gap. It's staying within that band, and then it goes back down into a different well within its band. That is a normal occurrence when it comes to quantum well infrared detectors. Now we're going to describe what goes on within those wells besides the absorption. So what occurs is the photon comes into the well, it then excites the electron, and within that it goes through a optical transition dipole moment, which means that it's transitioning from energy states. That transition of energy states will allow it to rise further up the well, so that's increasing its potential. While it's increasing its energy and its potential, the electron then moves out of the well and then tries to occupy another unoccupied space. And the cycle just continues. And then the photon comes in, does the same thing with the transition dipole moment, electron's on its way. It's very simple, it's not too complex. There's different types of quantum wells. There's asymmetric quantum wells, there's symmetric quantum wells, there's single, there's multiple quantum wells, and from there, they're all using the same process. The only thing that's really different is the amount of energy or the transition between the energy states that's required for the electron to be moved out of that well. The complicated one is the asymmetric couple stepped. So that means that there's different levels within the well, but one side is asymmetric and the other one is symmetric, meaning it's split down basically in the middle, and it's some type of drifting within the electron for it to occur. Within those, there's this thing called the dark current, which means that there is no transition, it's transitioning horizontally. The electron is transitioning horizontally. Instead of it going vertically, up and down, the dark current just pushes it up horizontally so it does not move out of the well. That means that electron is pretty much trapped in there, which dark current means it's not useful. So you're trying to negate dark current within those wells. And that's just something that's usually common within the more complex wells, but not necessarily unheard